How's everybody doing? Straight from West Virginia. Alright, let's get joke of the day, because it's the best part of the day. So, I need to look for my missing watch, but I can never find the time. Threw JD off because it was so bad.
It's getting worse and worse.
Anyways, all right, we're going to wrap up quadratic equations with this video. So we've looked at quadratic equations, what they are. We've looked at the 4 methods for solving them. And I want to give you some applications now. At this point, I've actually given you some applications because remember, when we were solving those quadratics, we were saying this allowed us to figure out where that curve, that parabola, was crossing the x-axis. That right there is enough of an application. But the ones that I want to show you now have nothing at all to do with a curve because everybody thinks that a quadratic only deals with curves, but it doesn't. So the first application that I want to walk you through is the idea of this Pythagorean theorem. Remember, the Pythagorean theorem applies to a right triangle. You know that you have a right triangle when you see the little box down here in one of the angles. That box indicates that you have a 90-degree angle there. When you have a 90-degree angle, that indicates you have a right triangle. So the Pythagorean theorem applies to right triangles. Now, almost everybody knows what the Pythagorean theorem is, and then go ahead and tell me. Yeah, I can hear you all the way through the camera. I can hear you. All right, so the Pythagorean theorem is a squared plus b squared equals c squared. Now, I prefer not to teach it as a squared, b squared, and c squared because a lot of people go, well, where's the a, where's the b, and where's the c? I'm not really sure. So what I prefer to do is I prefer to call it leg squared plus leg squared equals hypotenuse squared. And what I like to say is those legs branch off of the right angle. Oh my gosh, I actually did it. See, I made my legs make a right angle. And so what happens is I've got a leg here and a leg here, both of these branching off of this right angle that you see right there. So that's how I get a squared as one of the legs and b as the other leg. And then c is going to be this hypotenuse, the leftover side that goes across from the right angle. So here's your Pythagorean theorem, but you'll notice that within that Pythagorean theorem, I've got squared terms. This is where the Pythagorean theorem actually likens to or is used within the idea of quadratic equations. So let me give you my first example of an application where I'm not going to do a curve at all. Now in this application it says that I've got a rectangular park and it is 6 miles long and it is 3 miles wide, and I want to know how long is a pedestrian route that runs diagonally across the park. Now I've said many, many times that whenever you have a word problem, the best thing that you can do is read it in its entirety one time just to get a feeling for what's happening, which we've just done. I know that I'm dealing with this rectangle shape, and I don't know about you, but for me a picture is worth 1,000 words. So what I'm going to do is I'm going to draw that picture of that rectangular park, and I'm going to label what I know in it. I know that it's 6 miles long, 3 miles wide. So I know that this side is going to be 6 miles, and I know that this side is going to be 3 miles. I also know that within a rectangle, these two sides are the same length, and these two sides are the same length. I also know that within a rectangle, I have right angles on every single corner. Now, the next part of this says I want to know how long is a pedestrian route that runs diagonally across the park. So in other words, I'm going to have a diagonal that goes like this, running through that park. Now, once I throw that diagonal in there, you can see that I have now created a right triangle. I can either look at the right triangle that's up here on the top, or I can look at the right triangle down at the bottom. If I use the one at the bottom, then remember, this is also 3 and this is also 6. Doesn't really matter which side I'm looking at because I'm just going to utilize the idea of the right triangle. Remember, when I have a right triangle, I know that I can utilize that Pythagorean theorem that says a squared plus b squared equals c squared, or like I like to do it, leg squared plus leg squared equals hypotenuse squared. So now I'm going to insert the parts that I know. Within this blue triangle right here, remember those legs branch off of that right angle. So I've got a leg here and I've got a leg here. So I'm going to have 3 squared plus 6 squared equals that hypotenuse squared. Well, 3 squared is 9, 6 squared is 36, and I know that 9 and 36 is going to be 45. Whoa, sorry about that. And so now I know that in order to get just the hypotenuse and not hypotenuse squared, I need to undo the squaring. To undo squaring, that means I'm going to take the square root, and I'm going to take the square root of the other side, because what I do on one side, I got to do on the other side. Squaring and square rooting cancel each other out. That gives me that hypotenuse that I wanted. And now I can deal with this square root of 45. Now remember, always simplify a radical if you can. I don't know what I would multiply by itself to create a 45. So what I'm going to do is I'm just going to try to break it down, break it down, break it down. Remember, I grew up in the 80s. So anyways, 45 is 9 times 5. This is why we looked at those roots and radicals and why we tried to figure out how to simplify radicals. And recall, I'm either looking for perfect squares or pairs. 9 is a perfect square, and I know that the square root of 9 is 3. So I can take that 3 out. Nothing I can do with the 5, so I'm left with the 5 underneath. And that's going to be the length of that hypotenuse. If you cannot remember that the square root of 9 is 3, then you can break the 9 up as 3 times 3. And then remember, when you do that, and I'm just going to write that up here, 3 times 3, here's the extra 5 in the back. And remember, the idea of looking for pairs, when you see a pair, you take one out and it dissolves the other one. So still the 3 will come out, the 5 will stay underneath. Because this is a real world situation, I need to include my units in there. These are miles, so it's going to be 3 square root of 5 miles as the hypotenuse. Now, you know that in the real world, you can't stretch out a tape measure and measure off 3 square root of 5 units. That doesn't happen. So in the real world, what you would do is you would just take 3 times the square root of 5, or for that matter, right back here, you would just punch in square root of 45 and get that on your calculator, which is approximately 6.7. Now, I rounded there because, remember, this is not going to be exact. And so in the real world, it would be about 6.7 miles. But we don't live in the real world. We live right here in this imaginary world that I'm dealing with. And so we're going to keep things exact. So we're going to take that square root of 45. We're going to simplify it to a 3 square root of 5. We're going to leave it like that. Because for our purposes, we want things to be exact. And quite frankly, in the real world, you want to keep things exact as much as possible. So any kind of estimation, you don't do it till the very end. But this is one example of being able to utilize that quadratic methods with quadratic equations, because I did have a quadratic right here. We utilized that square root property. We isolated our squared term, and we took the square root of both sides. So that, again, is that square root property. So I'm going to give you another example of being able to use quadratic equations, and it's going to have nothing at all to do with a curve. So let me flip this over and get that example written. And once again, enjoy that scenery as I get this example written up here. So in this example, what's going to happen is we've got the base of a 30-foot ladder. And that base is 10 feet from a building. And if that ladder reaches the flat roof, we want to know how tall is the building. So remember, I've told you guys that if you have a word problem, read it in its entirety one time to just get a feeling for what's happening. We did that already. We know that we're dealing with this building and a ladder leaning up against the building. And remember, picture's worth 1,000 words. Do not ever be afraid to draw a picture of what's happening. So in my picture, here is my building. here's the ladder that's leaning up against, and it says that the ladder reaches the flat roof. So here it's reaching that flat roof, and here's my building with all of its windows. And so I know that it says the base, it says the ladder is 30 feet. So I'm going to label this side, that here's my ladder that's 30 feet. And it says the base is 10 feet from the building. So if I come out from the base of the building, this is 10 feet. Now, this creates a right triangle. How do I know that it's a right triangle? Because in order for this building to stand up and not fall over, it has to be perfectly vertical with this horizontal ground. This has got to be a right angle, and if it's not, that building's going to fall over. So here's my right triangle, and once again I can use that Pythagorean theorem now that I know that I have a right triangle. So once again I'm going to use my legs squared plus legs squared equal to my hypotenuse squared. And now when I fill my numbers in, I know that one of the legs, remember the legs branch off of that right angle, so one of the legs is 10. But here's the other leg. I don't know what it is. So I can either leave it as legs squared or I can call it x squared. And I know that my hypotenuse is 30. Now I know that 10 squared, 10 times 10 is 100. And I know that 30 squared, 30 times 30 is 900. Now I want to get that x all by itself so that I can take the square root. Here again comes that square root property. So I'm going to subtract that 100 from both sides. 900 minus 100 is going to be 800. And now I'm ready to take the square root of both sides because I've isolated my squared term. So I'm going to take the square root of this, squaring and square rooting cancel each other out. I've got my x all by itself. I'm going to take the square root of this side as well. Since I don't live in the real world and we're dealing with this imaginary little world that we're working in, I'm going to simplify that radical because I can't think of what I can multiply by itself to create an 800, but I do know that 800 is 8 times 100. Maybe you thought of something else, but I thought of 8 times 100. Now, the square root of 100, I know that's 10. So I'm going to take the square root of that 100 out. So the 10 is going to come out. And when I do that, I'm going to slide this over this way. I will get 10 square root of 8. However, I can break up that 8. 8 is 4 times 2. So when I do 4 times 2, I know that the square root of 4 is 2. So I'm going to take the square root of this 4 out, which is 2. I'm going to combine it with that 10. And recall that when I combine it with the 10, this is one great big huge multiplication problem. So what I'm going to do at that point is I'm going to take the 2 that's coming out from the 4, combine it with that 10 by multiplication, and 10 times 2 will give me 20. And this 2 is going to stay underneath. So here's my answer, 2 squared root of 20, keeping it exact because we don't live in the real world, we live in this imaginary world. But because it is a real world situation that I need to include my units, notice that it's feet. So the building is 20 square root of 2 feet tall. And again, if you wanted to map that out in the real world, you would take 20 times the square root of 2, or for that matter back here, square root of 800, and you would get approximately 28.3 feet. But again, that's approximation. That's why I put, it's not a straight equal sign, it's that squiggly little equal sign, but that means approximately equal to. Because as soon as I take the exactness out of here and I throw the decimal in there, because remember, this is an irrational number. That's going to go on forever and ever and ever. It's never going to repeat, never ends. Same thing here. So as soon as I do this and suddenly give an ending to that decimal, then I'm now approximating. So I cannot say it's equal anymore. It's going to be approximately equal. But there's yet another example of being able to use quadratic methods in order to solve this problem, because I once again did that square root property. So now I've got 2 more examples to show you just to be sure that we understand all the uses here. And so let me, don't know why I flipped that because I'm still going to have to erase. I could have erased the other side. I don't know. It's all good in the hood. We're okay. So, third example that I'm going to give you says that we have a rectangular parking lot And I know you may be thinking, oh my gosh, we've done this before, why are we doing this again? But it's because this one's going to handle differently. But my rectangular parking lot, got a different situation happening here, has a length that is 3 yards greater than the width. And the area is 180, well, the area of the parking lot. I should put that in there. Of the parking lot is 180 square yards. Area is always square units. We want to find the length and width. So once again, what we've done here is we have read it in its entirety to get a feeling for what's happening. We know, again, we're dealing with a rectangle, so a picture's worth 1,000 words, and I'm going to draw my rectangle in here. Now, I also know that the length is 3 yards greater than the width. So that means that if the length is greater than the width, this must be the length, this must be the width. So here's my length, here's my width. So what that means is I should be able to take this width here, I should be able to add 3 more yards to it, and when I add 3 more yards to it and it's about this long, I should be able to make it the same thing as the length. Now I know this didn't work out very well, but that's the idea here, that if it says that it's 3 yards greater than the width, I should be able to take this, tack on 3 more, and that, when I compare it to this, should be the same. So what that means is the length is 3 more yards than the width, or 3 greater than the width. Is always means equals. So the length equals 3 yards plus the width, and that's how I get this right here. Now, the next part of this says, I know the area is 180 square yards. Well, how do you get area of a rectangle? The formula for area of a rectangle is going to be length times width. And I was told that that area is 180. So right here, this is 180. But the problem is I cannot solve this because I've got too many variables in there. When I have one variable, I can solve it. But I got 2 variables, so I'm stuck and I can't do anything with it. That's where this comes into play. Because I was told the length, or I figured out anyways, the length is all of this. So if the length is this, that means everywhere I see length, I should be able to put this in its place. So I should be able to take all of this and plug it right there where that length is. So if I plug it in there, then that means I'm taking that length out, I'm literally putting this in its place. Aha! Now I've got one variable and I can solve it. Now be very careful because everybody goes, oh yeah, remember that method of factoring said when I got 2 things multiplied together, either this one's going to be it or this one's going to be it. But that's only the zero product principle. When 2 things are multiplied together to get a 0, either this is the 0 or this is the 0. That is not at all what I have here. So when I multiply this times this and get 180, well, this could be an 18, that could be a 10. Or this could be the 18, that could be the 10. Or this could be a 90 and that could be a 2. Or this is the 90, that's the 2. Or maybe this is a 60 and that's a 3 and that's a 3 and that's a 60. There's so many different variations of this. So with that, I need to make this look like a quadratic that I can solve. And remember, all those 4 methods said pretty much, let's set it equal to 0. So that's what I'm going to do, is I'm going to multiply this out, and then I'm going to set it equal to 0. So when I, when I distribute the w through, because I want to be able to go back and use any of those 4 methods for solving a quadratic, I will get w squared plus 3w And now what I'm going to do is I'm going to slide that 180 over here so that I can start using any of those 4 methods for solving a quadratic. Now when I slide that 180 over, I'm going to subtract it. And now I'm ready to use any of those 4 methods. Sure, nearly everybody's going to settle into that quadratic formula because everybody thinks that's the easiest way to go, but I'm telling you, I will argue with you to my grave that if this thing will factor, that is the easiest way to do this. So I'm going to attempt to factor it. You guys who are using that quadratic formula, I'm telling you, I'll get there faster than you will. So when I factor, remember, I always look first to see if there's something common I can divide out before I do anything else. There is nothing common to all 3 of these terms. So I'm headed to that double parentheses. I know that this splits up as a W and a W, and I know that this back sign here tells me my signs are going to be opposites. One's a plus, one's a minus. So make one a plus, make one a minus. I want 2 numbers that are going to multiply for 180. They're going to subtract for a 3 because this being a 1 here, and that tells me I can do that. Multiply for 180 and subtract for a 3. That's going to be a 15 and a 12. So if I put my 12 here and my 15 here, notice out here I'm going to get a negative 15W and here a positive 12W. That gives me a negative 3W. That's not what I wanted, but I had the right number, wrong sign. So all I have to do is switch up my signs and that'll get it right for me. Now I get a positive 15W minus 12W. Yep, that's a positive 3W. And sure enough, 12 times 15 is 180. So now I can use my zero product principle that says when I've got something times something else, these 2 things, these 2 parentheses are being multiplied together to create a 0. One of these 2 parentheses has got to be the 0. So either this W minus 12 is the 0 or the W plus 15 is the 0. Now if the W minus 12 is 0, we add 12 to both sides, W is going to be 12. If the W plus 15 is a 0, we subtract 15 and we get a negative 15. Now normally we would just circle both of them, we're excited, we did it, we got it, we would put our units in there, we'd call it done. But remember, this is a real world situation, so we got to think about this. Use your good brain that God gave you and think about this. This says the width is 12 yards. This says the width is negative 15 yards. Does any of that not make any sense at all? And you're absolutely right. It makes no sense to have a negative width. So even though mathematically, technically, this is right. If I would plug a negative 15 here and here, then I would come up with 180. Because a negative 15 plus 3 is a negative 12. And a negative 12 times a negative 15, negative times negative is positive. And mathematically, theoretically, it works. But this is not theoretical, it's a real world situation. So that is what we call all of a sudden I blanked out. That is a solution that it's theoretically correct, but it doesn't work. So therefore, this is going to be my only solution for that width. So my width is going to be 12 yards. Now remember, I was told to find the length and the width. I found the width, now I need to get the length. But I have a couple of options to get that length. One option is to go right back here and say, okay, well if I take a 12 and add a 3, that will give me that length, which will give me 15 yards for my length. The other option is to say, well, let's take that 12 and let's divide 180 by 12, and that'll give me 15. And the great thing about this is this allows me to check my work and make sure that it's right, because 15 times 12, sure enough, is 180, giving me the correct area. And sure enough, 15 is 3 yards greater than that width. So I know, in fact, that this is right. So let me give you one more example of being able to utilize our quadratic methods for solving situations that have nothing at all to do with the curve. I had no curve here at all. It was a rectangle. It was straight lines on this. And so that last example here, again, I have no idea why I'm flipping this around because I'm going to need to erase this. I don't know. It'll be all right. But let me get this erased, and we will take a look at our last example of an application of quadratic processes that have nothing to do with a curve. All right, so here's our last example of applications of quadratic equations when it has nothing at all to do with the curve. So in this example, it says that each side of a square is lengthened by 2 inches. The area of this new larger square is 36 square inches. We want to find the length of the original square. So once again, the method or the steps to solving a word problem, or you need to read it in its entirety just to get a feeling for what's happening. We've done that. And remember, again, a picture's worth 1,000 words. So I'm going to draw that picture. So what happens here is I've got this square to begin with. And so here's my square, and I know that in that square every single side has the same length. And then it says I'm going to take this square, and it says that I'm going to lengthen each of those sides by 2. So when I take the sides and I lengthen them by 2, suddenly it creates a bigger square. And it says, okay, I'm going to take each of these original sides and I'm going to add 2 to it. So I'm going to take this side right here and add 2 to it. So I know that whatever this is, I'm going to add 2, and that's going to give me the length here. So the question is, do I know this original length on this square? And I don't. So when I don't know what it is, there's my unknown, and as soon as I have that unknown, I'm going to call it an x. So I know the side of this square is going to be an x, so I'm going to let x equal the side, or the length of the side of the original square. Length of side of original square. So then what that means is, in my new square, I'm going to take that side x and I'm going to add 2 to it. And because this new one's a square as well, that means all the sides are the same. So this is x plus 2, and this is x plus 2, and this as well is x plus 2. So now the next part of the question says, okay, that's what's happening in the new square. It says the area of this new larger square is 36 square inches. So I have to ask myself, all right, what does it take to get area of a square? Very similar to area of a rectangle. Area of a rectangle is length times width. It's just in this square, that length and that width are going to be the same. So in this big square out here, I know that that area is 36 square inches. But when I multiply the length and the width, I've got an x plus 2 times another x plus 2. And here's where I told you guys before, be very careful, because a lot of people do is they say, okay, that means I've got 2 things multiplied together to get a 36. Some will say that means either this is the 36 or this is the 36, but you can't multiply 36 times 36 to get a 36. So then some people will say, well, then that means that this is, say for instance, a 12 and that's a 3. Or maybe this is the 12 and that's the 3. Or maybe this is a 9 and this is a 4, or this is the 9 and this is the 4. So see, there's lots of different combinations. This, again, is where we need this set equal to 0 so that we can factor and use our zero product principle. So what I'm going to do instead then is I'm going to FOIL this out. And when I FOIL it out, I get x squared plus 2x plus another 2x plus 4. When I combine these like terms, I get x squared plus 4x plus 4, and that's equal to 36. But now what I'm going to do is I'm going to slide that 36 to the other side so that I can solve this by factoring. Now when I slide that 36 to the other side, I get 0 equals x squared plus 4x, and 4 minus 36 is a negative 32. And now what I'm going to do is I'm going to factor this in order to figure out what x actually is. So when I go to factor it, I'm going to slide that up right here. And actually, I don't have to factor it. I've got any of those 4 methods. I can complete the square, I can do the quadratic formula, I can factor it. I'm not going to do square root property because this first power term right here is preventing me from just simply taking the square root of both sides. So lots of people are going to settle in on the quadratic formula, but again, let me stress to you, if this will factor, that is the fastest and the easiest way to go. So I'm going to attempt to factor this, and so I have 0 equal. Now there is nothing common that I can divide out of every single term, and you always do that first. Nothing common here. So I'm going to head for that double parentheses. And when I head for that double parentheses, I know that this splits up as an x and an x. And I know that this means my signs are going to be different. One is a plus and one is a minus. Now I want two numbers that will multiply for 32. They're going to subtract for a 4 because I've got different signs. That's going to be an 8 and a 4. So I have a positive 8 here and a negative 4 here because out here I get a negative 4x and here a positive 8x. Those do combine to be the positive 4x. So now I do have a situation where I've got two things multiplied together to get a 0. So one of the two has got to be a 0. That's the only way to multiply and get a 0 is for one of the two factors to be 0. So either this x plus 8 is 0, in which case x is a negative 8, or this x minus 4 is the 0, in which case x is going to be a 4. Here again is the situation where we say, okay, that x was the length of the side and makes no sense to have a negative length. So this has to be the length of that side, and my units are inches, so it's going to be 4 inches for the length of that side. I can double check this to make sure that it's right, because if I take 4 inches and I add 2 to it, then I get 6. So 6 on this side, 6 on this side, 6 times 6 in fact is a 36. And so that makes sense, and this is how you solve that problem. So hopefully you're seeing that, like I said, quadratics do not always mean that you have a curve. It's a great application to take a curve and find the x-intercept where it crosses that, where your curve crosses the x-axis. That's one of the most common uses and applications of your quadratics, but you can see a lot of these examples don't have anything at all to do with a curve, and yet quadratic methods will get us there. So I hope that makes sense, and you guys have a great day.